I'm Dr. Lakshmi Ravishankar, and in this module we shall be discussing Claisen rearrangement and just look at a few examples of Yin reactions. So at the end of this module, the student should be able to identify a Claisen rearrangement, write the products of a Claisen rearrangement, predict the stereochemical outcome of a Claisen rearrangement, also write the product of an aromatic Claisen rearrangement, should be in a position to identify an Yin reaction and draw the product of an Yin reaction. So Claisen rearrangement is another example of a 3,3 sigma tropic shift. We already saw the Cope rearrangement in the previous module. So what happens in the Claisen rearrangement? You basically have an allyl vinyl ether, or it could also be a phenyl allyl ether, which isomerizes to a gamma delta unsaturated carbonyl compound if you are taking an aliphatic allyl vinyl ether. And if you take the phenyl allyl ethers, then you end up with an ortho allyl substituted phenols. The Claisen rearrangement was first reported by Claisen way back in 1912, that is almost 108 years ago, and it was an example of an aliphatic allyl vinyl ether which undergoes rearrangement to give me a gamma delta ketone. Unlike the Cope rearrangement, which was only having a carbon in its framework, the Claisen rearrangement also has oxygen, and it involves formation of a strong carbonyl bond in the product. And since the carbonyl double bond, C double bond O, is much more stronger than the C double bond C, the products of the Claisen rearrangement are highly favored at equilibrium. But how do we know exactly that the reaction proceeds through a concerted mechanism involving a 3,3 sigma tropic shift and not a polar mechanism? And this has been done by doing labeling studies. So if you take this allyl aryl ether and you have this carbon which is attached to the oxygen as labeled, that is, it is isotopically labeled, then if it were a concerted mechanism, this should be occupying this position and it cannot be coming anywhere else in the product. And it has been found that when you do the Claisen rearrangement of this, the labeled carbon does come and it occupies this terminal carbon position of the allyl in the substituted phenol. So these results indicate that the Claisen rearrangement indeed proceeds by a concerted mechanism. Let us see the stereochemical aspect. So if this is my starting allyl vinyl ether, the relative stereochemistry across the new carbon single bond is established as a result of the chair-like. Now recollect, in Cope rearrangement also we talked of a chair-like transition state. So this is also a 6-electron system. So this also proceeds through a chair-like transition state. Only difference is one of the atoms is going to be oxygen, unlike in the Cope where all of them were carbon. And it depends on the geometry of the double bonds in the starting material. So suppose you had the double bonds like this, that means this is pointing in the upward direction, this is going downwards, and or in other words, this is my E and this is also EE isomer, or if you take the ZZ isomer and you do the Claisen rearrangement, you find that the two methyls, it goes through a cyclic transition state and the two methyls are going to be trans to each other, and you know that trans 1,2 trans could be diaxial or diequatorial, but it would be preferring the diequatorial orientation, and this would be the product and the stereochemical outcome of the ketone that you get after the Claisen rearrangement. Now here if I take this double bond is going to be E and this double bond is going to be Z. So you're talking about the EZ isomer either in this way or in this way. The product you get is going to be a cis product. In other words, the two methyls are going to be cis to each other, and 1,2 cis in a cyclic transition state would be one axial and one equatorial. So similar to your transition state which we saw in the Cope rearrangement, here also the stereochemical outcomes is going to be similar to that, since the transition state model is the same in both of them. Both of them are having the chair-like transition model. The same thing we have shown here. So suppose you have, this is my starting compound for the Claisen rearrangement. This is the chiral carbon. Now if you see here, this is this attached to carbon with Y, the ether oxygen. So this is going above the plane, so this has to be equatorial, And if you form a bond here, this shifts here, this shifts here, okay, and you will see that this is going to be the product that you get. So the R1 that you have here is now going to be pointing in this direction, or in other words, the stereochemical outcome for this double bond, it is going to be having the E stereo descriptor. Now, if you have an allyl phenyl ether, then also it can undergo the Claisen rearrangement, because you see this part of it is going to be like your vinylic group. However, when this undergoes rearrangement, you're going to get this keto product, dienone product. Now, one would wonder, why should this be formed at the expense of the loss of aromaticity? Okay, but the equilibrium would still lie towards this due to the formation of the carbonyl bond. However, this will immediately undergo tautomerization, which is not a concerted process, to give me the 2-allyl substituted phenol. So the carbonyl quickly tautomerizes by a non-concerted mechanism to the aromatic 2-allyl phenol, and this, however, cannot undergo reaction in the reverse direction. What happens if both the ortho positions are blocked? Then in that case, the rearrangement occurs at the para position, and that is known as the para-Claisen rearrangement. But please do not think that this bond is migrating from 1, 2, 3, 4, 5, or it's a 1-5 migration. It goes through two sequential 3-3 sigmatropic shifts. The first one is your normal Claisen rearrangement to give me this intermediate. Now if you see here, this is 1, 2, 3, 4, 5, 6. So it is a 1,5 hexadiene system, which will immediately undergo a cope rearrangement. So that is the second 3-3 sigmatropic shift to give you this dienone, which will tautomerize to the phenol. So the direct 1,5 shift mechanism is unlikely because of the distance between the oxygen and the para position. So it has been demonstrated to proceed by two successive 3-3 shifts. The first is your conventional Claisen rearrangement, and the second is your cope rearrangement. And once this is formed, this immediately undergoes tautomerization to the phenol, which is a non-concerted process catalyzed probably by acids or bases. Now, what is the proof that there are 2-3-3 sigmatropic shifts involved? This intermediate, which is formed after the first Claisen rearrangement, you see now this is a diene. If I have a dienophile, this can easily undergo a Diels-Alder reaction, and indeed this has been trapped in a Diels-Alder reaction, and that shows that the first step involves a conventional Claisen rearrangement to give me this dienone product. Even if the ortho positions are free, it has been found that some amount of para product is formed. But however, if you have your allylic system is a conjugated system, as is seen here. Now you see this carbon is close to the para position, so it can undergo directly a 5-5 sigmatropic shift. So this comes here, shifts, and you see that you get the para-Claisen rearrangement directly without going through 2-3-3 sigmatropic shifts. We just come to the last part, and that is a group transfer reaction, or also known as an Ene reaction or the Alder-Ene reaction by its discoverer Kurt Alder in 1943. It basically involves a chemical reaction between an alkene which has got an allylic hydrogen, which is known as the ene, and an enophile, which is nothing but an other alkene or a molecule with a multiple bond. And you form a new sigma bond. So this is the new sigma bond which is formed here with the migration of the ene double bond. So the ene double bond has migrated here, and there is a 1,5 hydrogen shift. Now please note 1,5 is 1, 2, 3, 4, 5. It is a bit different from the 1,5 sigmatropic hydrogen shift which we saw in the previous module, where it was intramolecular. Here it is an intermolecular migration. So these are some examples where this hydrogen is picked up here, this forms a bond here, and this becomes a double bond here. Similarly, you have 3 allylic carbons these methyls are allylic carbons, so they have hydrogens which can be transferred here to give you this adduct. Like I said, it need not be, the enophile need not be only an alkene, it can be a triple bond also. So this hydrogen is transferred here and you get a bond between this carbon and this carbon with the simultaneous migration of this pi bond. So these are some examples of the ene reactions. Again, it involves 6 electrons, 2 plus 2, 4 plus 2, 6. So it is a 6 electron, a 4n plus 2 pi electron proceeding through an aromatic cyclic transition state. So to summarize, Claisen rearrangements are 3,3 sigma tropic shifts which involve allyl vinyl ethers to give gamma delta unsaturated carbonyl compounds. They are thermally allowed superficially and proceed through a cyclic 6-membered aromatic transition state and proceed through a chair-like transition state. Aromatic Claisen reactions involve allyl phenyl ethers and yield ortho-substituted phenols after initial 3,3 shift to the ortho position followed by tautomerization to the phenol. However, in case your ortho positions are blocked, then the migration takes place to the para position by a sequence of 2 3,3 sigma tropic shift. The first one is a normal Claisen rearrangement and the second one is the Cope reaction, and this is known as the para Claisen rearrangement. Ene reactions or group transfer reactions are reactions between an alkene containing an allylic hydrogen, which is known as the ene, and another alkene or a multiple bonded system known as enophile, with the formation of a new sigma bond and migration of the ene double bond followed by a 1,5 hydrogen shift. So with this we come to the end of sigma tropic rearrangements. In the next module, we'll try to see applications of pericyclic reactions. Thank you.